In a 21st century battle space, as enemy defensive capabilities continue to improve, the ability of either an unmanned or manned aircraft to defeat an incoming threat with conventional means will continue to diminish. Aptima Inc. is developing novel artificial intelligence, AI models, that can predict future actions of the adversary forces, including positions of their assets, their capabilities, the battlefield maneuvers, and mission intents. Under the Navy's SBIR program, our team is developing Alice, a machine learning solution for unmanned vehicles to infer adversarial behaviors and create efficient counteractions. Alice's main innovation comes from the ability of AI to explain observations about the enemy, evaluate its internal uncertainty, and probe the battlefield environment and enemy responses, and do so interactively and with limited supervision. The role of the human is changing in the presence of an amazing wave of artificial intelligence. The paradox is that the more automation we introduce, the more critical the role of the human becomes. AI forces us to be more precise about the way we learn, the way we train, and the way we work. With this paradigm shift, Aptima is helping individuals, teams, and organizations keep pace, adjust, learn, and perform in this exciting new era. Our work also results in changing how the AI learns about its world, endowing the AI systems with cognitive processes and adaptive characteristics of the humans. In the last few years, the AI-based systems have achieved unprecedented levels of sophistication, often outperforming expert humans on complex decision-making tasks. From autonomous ground robotics to large foundational models generating natural language, realistic videos, writing code, or solving complex logical problems, the AI-powered technologies are becoming omnipresent in our daily lives. AI models also have a high potential to transform the 21st century battle space. The employment of autonomous vehicles, or UXVs, both in the air and sea, is no longer the distant future. However, such systems are typically controlled individually, unable to coordinate joint tactics. The automation on any UXV is extremely structured, limited to path planning, target identification, and simple seek-to-destroy actions. If the situation deviates from the planned mission, the operators take control from the automation. AI technologies can transform the large collection of robotic systems into a cohesive force. Realizing this vision, Aptima Inc. is developing Alice, a set of machine learning analytics that allow autonomous systems to learn, coordinate, and adapt in the complex dynamic battlefields. Alice will support the Navy's autonomy programs by providing AI capable of acquiring knowledge and generating superior plans by learning to read the adversary. Alice supports and enhances automation of UAS platforms by learning a representation of the enemy's operational dynamics, capabilities, and intents that maximally explain the observed actions. Alice then evaluates the uncertainty of such representation and incorporates it in selecting actions for the friendly assets. This allows our AI to optimally balance exploitation and exploration. Exploitation is based on maximizing external rewards, such as satisfying mission goals and reducing the risk to friendly assets. Exploration is achieved by maximizing the reduction of uncertainty in its learned representation. Alice is able to reason about the actions it selects, building the beliefs about future enemy actions and the battlefield effects, and estimate the impact of its own plans on such beliefs. Consequently, the action decisions produced by Alice are supported by deliberations that resemble human cognitive processes and can be explained to and understood by operators. Alice represents a novel AI-based multi-agent control methodology that jointly solves the sensing, battlefield understanding, and action generation problems using self-supervised approximate Bayesian inference. This results in an explicit perception learning prediction control cycle, during which our AI system builds beliefs about past and future states of the enemy's forces, acquires knowledge about the enemy's intents and behavior by inferring hidden states and dynamics, observation signals, and action preferences, and automatically generates a sequence of actions to simultaneously achieve mission objectives and resolve uncertainties about current knowledge and beliefs. In the case where a UAS is at risk from a potentially lethal engagement by one or more threat systems, its action planning must be robust against alternative enemy operations and tactics. Such capability requires predicting a lethal outcome, automating optimal implementation of countermeasures, and finding how to egress to a standoff location or non-hostile terrain. Current methods of surviving an engagement are dependent on precise maneuvering and countermeasure response, and rarely anticipate follow-on threat activity. As the enemy can change its tactics, so should the friendly forces, requiring the AI-based automation to be adaptive to such changes. Alice-produced actions for Blue UAS entities will be both robust and adaptive to uncertainty and changing tactics of the adversary. Alice decision-making and selected actions will be robust because our solution accounts for alternative enemy states, actions, preferences, and evolution alternatives, and will be adaptive because we continually, intelligently, and incrementally update knowledge and action policy while seeking observations to optimally reduce uncertainty in the operational environment. Such capabilities are possible because Alice Framework for Action Generation is based on a solid foundation, a theory of active inference, AIF. The AIF is a generative model that integrates acting and situation understanding in dynamic, uncertain environments, which emerged in the late 2000s as a theory of brain function and later developed into a unifying framework for perception, action, and learning. It has been used to simulate a wide range of behaviors in neuroscience, machine learning, probabilistic control, and robotics. AIF stipulates that to achieve adaptive behaviors, the biological systems must continuously learn and update a probabilistic model of their operational environment and act to receive sensory inputs to maximize the evidence for this model. AIF explains that perception, action, and learning are emergent processes of approximate Bayesian inference to minimize environment uncertainty. Implementations of AIF are supported by considerable empirical evidence and can be effectively applied to Navy's high-dimensional tasks and environments. While many recent AI models achieve tremendous success in solving complex, multi-agent decision-making problems, such as reinforcement learning and encoder-decoder causal decision transformers, the AIF foundations provide much higher sample efficiency due to its ability to evaluate uncertainty and account for it when selecting information-seeking actions. As a result, Alice will create the AI that is able to self-train in an interactive, continuous manner, be more efficient at generalizing and transferring knowledge across tasks, and not require millions of experiences or annotated data samples to obtain sufficient automation skills. Initial implementation and testing of Alice Analytics included three main components. First, we used the Next Generation Threat System, NGTS, to model the battlefield in which the Alice AI controls multiple unmanned systems against the adversaries. The Alice analytics are wrapped in the inference engines that generates the representation of red behaviors, inferring their capabilities, intents, states, and generating blue actions. To produce the effective inferences, Alice uses the generative model, which corresponds to internal simulation module. Using internal simulation, Alice executes counterfactual reasoning, internally testing potential past situations and imagining possible futures. Using this information, Alice is able to identify a sequence of most impactful blue maneuver and weapons employment actions that allow the controlled assets to simultaneously achieve mission goals, reduce risk, and obtain informative, novel observations to reduce uncertainty about the battlefield. Our original ideas were to support the human operators conducting mission planning. In this manner, Alice AI would provide the reasoning and battle management for the units in the environment, with Aptima engineers building models that can assist the tasks of planners. Such capability could be deployed as automated adaptive red forces for the battlefield simulations, or the functions providing construction of the adversarial and friendly tactics and courses of action. The Alice system was planned using multiple spirals, starting from the theory and concept development, and undergoing several stages to implement and validate functional components. The project is currently wrapping up Phase 2, Option 2. During initial phases, we use the NGTS as the virtual environment testbed for Alice AI. We showed ability to learn the movements of red unmanned aerial vehicles, infer their state from sparse observations, and reconstruct their behavior structures encoded in the behavior transition networks, BTNs, the state machines used to control virtual assets in NGTS. While high-fidelity simulations like NGTS can be run 100 times faster than real time, their simulations are still insufficiently fast for conducting experiments and AI testing at scale. Moreover, the NGTS does not provide easy runtime APIs and abstractions available to AI researchers via Gymnasium Python environments. Accordingly, during follow-on work, we switched to using a close air combat simulation environment, a fully Pythonic simulation supported by JSB-Sim physics engine for modeling aerodynamics of UAS platforms. Alice-based AI agents can now learn and be tested with the full support of extensive open-source libraries for developing and managing deep learning and reinforcement learning multi-agent planning analytics. As the AI development progressed, large foundational models showing promise and providing needed computational tools, while the multi-agent reinforcement learning algorithms still maturing, the rigorous testing of AI automation for multi-agent mission planning is necessary and feasible. The space of observations, complexity of the defensive and offensive operations, diversity of the decision-making tasks, advances in flying dynamics, and cost reduction of aerial platforms, and availability of deep learning toolboxes now allow faster workflows for building and testing AI systems needed by the Navy. Researchers and subject matter experts in military decision-making can now jointly build the virtual wind tunnels for AI autonomy supporting the multi-domain operations. The development of the AI solutions can exploit the wide availability of open-source multi-agent environments and libraries of single-agent and multi-agent algorithms. As we fully validate the Alice's ability to control and adapt to intelligent adversaries, our team is working to integrate our analytics with advanced framework for simulation, integration, and modeling, AFSIM, and eventually deploy our AI on physical platforms such as MQ-4C Triton and MQ-9B Sky Guardian. We believe that Alice is an exciting solution to automation for unmanned platforms. Please contact us using the email or phone numbers below for a demonstration or a detailed capabilities briefing. Thank you for your time, and we at Aptima Inc. look forward to your call.